Hello everyone, welcome to my video series on statistical significance testing. So in this video, we are going to talk about the Pearson correlation test. So quite a while ago, we talked about the Spearman correlation test. Pearson correlation is basically the parametric version of that correlation test. So let's dive in. So first of all, let's start with an example. So you can see three graphical plots here. So in each case, we have an x variable where we have some values. We have 5 values here in total, and we have the y variable. We also have 5 values in total. So we are plotting these xy points right here. You can see that when x increases, y also increases in this particular plot. So they are positively correlated, and correlation coefficient R is equal to 0.98. I'm going to show you exactly how to calculate this a little bit later on. But here you can see that the points are not really very well correlated. X and Y aren't very well correlated. That is why R is equal to only 0.3. In this case, when X increases, the Y decreases linearly, and that is why R equal to -1. Remember that for Pearson correlation, the coefficient value can be from -1 to +1. That is the entire range of Pearson correlation coefficients. Now the question is, how do we calculate correlation R between X and Y? That is number one. And number two is how to see if the correlation that we have measured is statistically significant or not. That means the p-value is low enough or not. So let's try to answer these two questions. So this is the first thing. So let's assume that these are the 5 X values and these are the corresponding 5 Y values. The first thing we have to do is we have to get the mean of X and the mean of Y, which is 3 and 5.2 right here. Next, we have to take this. We have to take X minus X bar, and we have to take Y minus Y bar, right? Okay, so after taking these two things, we will take their product. That means X minus X bar into Y minus Y bar, minus 1 into minus 1.2, 0 into minus 0.2, and so on and so forth. So these are the products. Now, we have done a lot of math, but what is the purpose of all of these things? The purpose is to get this Pearson correlation coefficient, and this is the formula. The formula may look very hideous at first, but it has some great intuition, which I will talk about next. So if we plug in these values right here, we are going to get R equal to 0.98. Okay, fine. Now, let's try to have an intuition of how this formula actually was derived. Let's assume that X and Y are two vectors. So in the X vector, we have all the X values. So in this case, there will be 5 values in this vector, and there will also be 5 values in this Y vector. So we can center them. We can center X and we can center Y by subtracting the X bar, which we have done here as well, and by subtracting the Y bar. So we have X sen and Y sen. Now, what is the cosine similarity? What is the cosine similarity between X sen and Y sen? The answer is it is nothing but the dot product between X sen and Y sen. And the dot product, this should not be called dot product. This is just multiplication of the magnitude of Xn and Ysen, right? So if you actually put in the values, it will look something like this. So yeah, the scalar form of this whole vector thing actually looks something like this. So if you know basic linear algebra, you are going to know that this and this quantity are exactly the same. Now, obviously, the goal of this course is not to teach you linear algebra. So hopefully you can search out some resources to see that this is indeed the case. Okay, now that you know how to get R, let's try to understand how you actually understand whether this correlation is significant or not. So the null hypothesis here is there is no correlation between the two variables X and Y, and the alternate hypothesis is there is significant positive or negative correlation between X and Y. Okay, now let's try to have an intuition of how we can do this. Suppose first we randomly pick n values for X and n values for Y and calculate R. So for example, if you have like 100 values in X and 100 values in Y, maybe you can pick 50 values at random from X and 50 values at random from Y. Obviously they are paired, XY pairs, so you can pick the 50 paired values and then get the R, right? Now you can do this many times. You can do this simulation many times and get many R values. Now the thing is, these R values that we picked right here will form sort of a normal distribution, which can be approximated by t distribution for a small number of samples. Now, if you know your distributions, the t-distribution and the z-score and the normal distribution, all of those things, you know that when we have a limited number of sample, normal distribution is actually approximated under the t-distribution, especially if your population standard deviation is not known, then this is indeed the case. Now, in order to have a better understanding about what I'm talking about right here, you should go back to the previous video, which is on the t-test itself. I will leave a link in the description later on. Okay, so what is the t-score? The t-score is nothing but signal divided by noise, right? So normally you are going to see some signal, that means some variable, subtraction or something like that. And in the denominator, you are going to see some kind of standard deviation, which is basically a symbol of noise, right? Okay, so what is signal here? Here the signal is R. Basically the correlation R is the signal. And the noise is nothing but 1 minus R squared and square root of that. That is the noise, right? So whatever is left is noise, basically, the noisy part. Now there is one more component here. So basically there is this thing called degrees of freedom, and it is going to be n minus 2. That means if you have 10 xy pairs, then degrees of freedom is going to be 10 minus 2 equal to 8. Now you may ask that typically we see n minus 1 as the degrees of freedom. So why are we putting n minus 2 here? So that is why I have drawn this plot right here. So this is basically what we are trying to do in this Pearson correlation, right? So we have these points right here, x and y are their values, and we are trying to feed a line, right? We are trying to feed a best fit line right here. And in order to feed that line, we need to learn A and B. That means slope and intercept, right? So we need to learn two things. Since we need to learn two things, we are preserving those two for the degrees of freedom, right? So that is why it is n minus 2. Now, t is equal to nothing but r, which is signal, divided by noise. Now, noise is going to be root 1 minus r square divided by root n minus 2, because obviously, as we have more and more samples, this noise is going to be reduced. That is why we are dividing this noise by n minus 2. And so if we just put it above, then this will be the formula of t-score. So if you just put in r, n, and two things right here, you are going to get the t-score. So typically, if you have a small r value, we are going to also have a small t value, obviously. That means there will be no extreme correlation. So we are going to have a large p value. So large p value means statistically not significant. Alternatively, or like vice versa, if you have a large R value, you are going to have a large T value, you are going to have extreme correlation, and so you are going to have small P value, and so statistical significance, right? I think this makes sense. For example, in our case, when R equal to 0.98 and N equal to 5, we are going to have a large T, which is around 8.6, and for this case, P value will be less than 0.01. Again, so obviously we're wondering that how are we translating this t-score to p-value? For this, definitely check out my previous video on t-test, the link of which I will leave in the description, because there I actually drew some graphs, some tables and all those things, and actually explained how to exactly get the p-value from the t-score, which is in itself a pretty big topic. So hopefully you will go through that 10-minute video to understand that first and then come back here. Okay, so again, for the second case, we have r equal to 0.3. In that case, t is approximately 0.57, and for that, p equal to around 0.6. And since 0.6 is bigger than 0.05, this is not statistically significant. For the last negative correlation case, the correlation is perfect. That is why the t value will be very large, and so the p value will be very small, almost zero. So the question is, when do we use the Pearson correlation? Because so far we have talked about two correlations. One is Pearson and the other one is Spearman. So when do we use Pearson correlation? First thing is when we expect linear correlation to happen, right? That means the metric of measurement for x and y are similar. For example, you can sort of try to correlate height versus height, or weight versus weight, or tumor fraction versus tumor fraction. So if there are those similar metrics of measurement and you expect the linear correlation, then you should use Pearson correlation. Also, x and y should be roughly normally distributed. I think this is an extremely important case, and many people forget about this. So if this is not really true, then you should be using Spearman correlation instead. And also, there shouldn't be any strong outliers, because as you saw before, that we are trying to fit a straight line, right? And the straight line is actually very susceptible towards the strong outliers. Finally, if you only care about data ranking, or if you only care about the ranks of the data, I mean, you don't need to really use Pearson correlation. But if you care about the magnitude as well of the data of x and y, then you can use, or you should use, Pearson correlation. So if you like the video, please feel free to subscribe and share. And if this video was helpful, you can join to our channel via the link in the description. Thank you very much.